Hi, my name is Grace Pryor.
My name is Daniel Perez, and this is our experiment on half-life of a muon, counting the cosmic rays using a DSLR camera.
Background. The lifetime of a cosmic ray muon on Earth is 2.2 nanoseconds, or about 670 meters, and then they decay into electron and neutrinos. Average energy is 4 giga-electron volts, and the typical intensity is 150 per square meter and second. There was an experiment done where there was 1 million muons created in the upper atmosphere. They plummeted 10 kilometers down to the Earth at a speed of 0.99 c. They have a half-life of 1.56 times 10 to the negative 6 seconds. And then it was detected that there were 49,000 muons detected at ground level. It was discovered that a large number of muons do reach the Earth, and this can be explained by time dilation. This is where t is a time measured in the laboratory system. T prime is the time measured in the rest frame of the system. V is the velocity of the system, and c is the speed of light. The half-life of a muon in a reference frame traveling with the muon is tau, equals 2.25 nanoseconds. Relative to an observer on Earth, however, the muons have a half-life equal to gamma tau. For example, for V equals 0.99 c, we find gamma equals 7.1 and gamma tau equals 16 nanoseconds. So with V equals 0.99 c, the distance traveled as measured by an observer on Earth would be gamma tau V equals 4,700 meters instead of 670 meters. This goes in the equation shown below. Cosmic ray particles are estimated to hit the Earth's atmosphere at the rate of about 1,000 per square meter per second. Cosmic rays are about 90% protons and 9% alpha particles, and the rest are heavier nuclei and electrons. Most of these rays are relativistic, meaning they have energies that are comparable to their masses, and only a small fraction of them have ultra-relativistic energies extending to about 20 joules. The far left image is a cosmic ray shower. It is an artist's drawing of cosmic ray hits. The center image shows heights that are particles produced after a hit, and the right image shows or labels the particles. The half-life of a muon. Stationary muons do not all live for the same amount of time. There is a random element in the decay process. This makes it impossible to calculate the lifetime of a single muon, but instead it is possible to calculate the average lifetime of a large collection of muons, which is what was done in our experiment. Elementary particles are not full of memory. The probability for a given muon to decay in a given period of time is completely independent of how long ago the actual muon was created. This leads us to our experiment. The setup for our experiment, or what we used, was a Nikon D600 digital single lens reflex, or a DSLR camera. The figure shown to the side was Daniel Perez and the experiment setup.
That's me.
Camera settings. We set the camera to the ISO, which equals 1600. Set the camera to manual M mode. Set the time to time or bulb. Set to JPEG. Set image size to large or L, and set the shutter to 2 seconds delay remote. Procedure. Cover the camera lens to make it dark. Set an image with the remote control button and stop after 10 minutes. Record image number, dates, times, and exposure times. Repeat with at least 3 more images. It is important that each image has the same exposure time, which should be close to 10 minutes. Then using the blink comparator, match the 2 images up and have them appear on the screen simultaneously to count the cosmic rays. Here we'll show you the software that we used. Here you can see them blinking simultaneously. One picture is behind and one picture is forward. You can kind of see where one of the cosmic rays is shown on one picture and one of them is not. And this is one of the ones that we counted right here.
All the way to the data. Alright, so we did 2 locations. We did here at Boulevard College and the other at my house in Hendersonville. At Brevard, we did it at April 29th around 8:30 a.m. and the elevation there was 653 meters. And the muons we counted on the blink capacitor for that one was 15. At Hendersonville, we did it May the 1st around 9:30 a.m. and the elevation there is 646 meters, and we counted 11. All right, so with knowing our muons at Brevard and Hendersonville, we can use this equation to try to find T prime. So we need to find first T, and we use this equation to find T by using delta H, which is the elevation differences between Hendersonville and Brevard, which is only 7 meters, and V, which is the velocity of a muon, which is 0.99 times speed of light. After we calculate it, we get T prime, and this is what we got for T prime. And then once we got T prime, we input it in this equation with gamma tau. We know that gamma is 7.1, and then we just figured out T prime, so we put them in and solve for tau, and this is what we got. So tau is the half-life of a muon. In our experiment, we got this, but the actual lifetime of muon is 2.25. So as you can tell, we were way off. Some of the errors, I'm guessing, is we could have either done our calculations wrong, but we also had a very small elevation difference. Our initial plan was to go to South Carolina, which there's actually a 300-meter difference, but we were having problems with the camera. The first time I did it, I did not take the pictures right. I didn't follow the procedure correctly. And then the second time I tried to take it, the batteries kind of ran out, so I couldn't get any pictures. So if we could do this experiment again, I would get a fully charged camera and try it again. And that was pretty much it. So overall, I guess we kind of failed the experiment, but it was the best we could do.
All right. Thank you for listening to our lab experiment.